Welcome back, everybody. In this video, we're continuing section 1.5 by looking at even and odd functions. So first of all, definition. For a function to be odd, what that means is that f of minus x equals minus f of x for all x in the domain of f. An example of that would be the function f of x equal to the cube root of x. Here, f of -8 is the cube root of -8, and that is minus the cube root of 8, which is -2. In a sense, you could think of for an odd function that the minus sign kind of pulls through the function symbol. Another example of that would be g of x equal to x to the 5th power. G of -2 would be -2 raised to the 5th power, which is -32. And that is minus g of 2. So the negative sign pulls through that minus, pulls through that function symbol. And that is an odd function. A function is even if f of minus x is f of x for all x in the domain of f. So rather than having the minus sign pull through the function symbol, it just kind of goes away. So an example of that would be our basic x squared function. For example, f of -5 is -5 squared, or 25. And that's the same as what f of 5 is. F of 5 is also 25. I think of the exponents here as a way to remember how an example of each of these functions. For the even function, x squared has an even numbered exponent, and it's an even function. For odd, g of x, for example, was x to the 5th, and it has an odd numbered exponent. Okay, another example of an even function. Let's let h of x be 1 over x squared plus 3. H of -2, 1 over -2 squared plus 3. Okay, that's 1 over 4 plus 3, or 1/7. And then h of 2 is 1 over 2 squared plus 3, which is also 1/7. For a even function, finding f of minus x is the same as finding f of x. For an odd function, f of minus x is minus f of x. Some functions are odd, some functions are even. A lot of functions are neither, right? So the function g of x, let's go a little thicker. The function g of x equal to x squared. Let's go with x plus 1 squared minus 3. This function will be neither even nor odd, okay? So to see that, g of minus x will be minus x plus 1 squared minus 3, and that's not the same as our original g of x. It's also not the same as minus g of x. One interesting thing about even and odd functions is how their graphs look. For a function that is even, like the x squared graph, it has a y-axis reflection symmetry. What that means is, if you were to take and fold the graph across the y-axis, like pictured on your paper, if you just fold it across the y-axis, the two halves would exactly line up with one another. For an odd function, it has a 180-degree rotational symmetry, kind of like a fan blade, okay? So that can be helpful when we're graphing functions. If we're able to know what half the graph looks like, we can use its even or oddness to help produce the rest of the graph. That would be one of the values in knowing whether a function is even or odd or not. So let's try that just for this little piece of a triangular kind of sawtooth function. If what we want to do, what are we to do, is just to finish the graph. So let's say that I've got this graph. All I've shown you is what the quadrant 1 part of the picture looks like. We want to think about what the rest of the picture is going to look like. So for the even function, what could be the rest of the picture? I know there won't be anything in quadrant 4 because that would make it so that it's not even a function. It would fail the vertical line test. So it's either going to be in quadrant 2 or 3. For an even function, the graph is going to be a reflection across the y-axis. So where on this one, its point is right here, it should be about the same distance to the left and about the same height. Okay, so that is a mirror image across that y-axis. It's an even function, so you do get that reflection symmetry across that y-axis. For an odd function, there is 180-degree rotational symmetry, so the graph will look something like that. It's as if you were to take the graph and rotate it around the origin 180 degrees, it would match up. So knowing whether a function is even or odd can help you to produce the graph if you know part of the graph. Okay, so one of the things that we want to be able to do is, just given the formula, we would like to be able to decide whether a function is even, odd, or neither. And so if you feel like graphing it, go ahead if you already know how to graph it. But usually we use the even and oddness to help us produce the graph. So that's kind of backwards. So what instead we'll do is we'll use that kind of algebraic criterion to see whether the function is even, odd, or neither. So let's try it here with 85. I want to find out what f of minus x is. Is it just f of x? Is it minus f of x? Is it neither one? So f of minus x, I'm going to take our rule for f, and I'm going to substitute in minus x in place of everywhere you see an x. And we'll have to do a little bit of simplifying to help see what it is that we've got. So minus x squared will be minus x squared. And then plus minus x is the same as minus x. And then to try to recognize what that looks like, I'm going to factor a negative out. If I factor a negative out, we'll get x squared plus x left over. And that should look familiar. Isn't that in parentheses just what f is? So it's minus f of x. So f of minus x is the same as minus f of x. Does that make it even or odd? It makes it even. Well, let's think. Is it even or odd? Well, let's think about what's happening. Our any possible y values would change to negative. So that would be a reflection vertically. So that means that the graph has to be odd, or the function has to be odd. So remember that for an odd function, the minus sign pulls through the symbol. For an even function, it just kind of goes away. And the kind of prototype we have of that would be maybe like the x cubed graph or x cubed function. If you have minus x cubed, that's minus x cubed. The exponent there is an odd number, so that can help you remember the name, that it is odd. All right. For 86, here I see an x to the fourth and an x squared, so it'll probably end up being even, but it's good to check. F of minus x will be minus x raised to the fourth power minus 4 times minus x squared. Again, with simplifying, this will give us x to the fourth minus 4x squared, and that is our f of x. So sure enough, it is an even function. Okay. Lastly, 90, f of minus x is minus x plus 1 over minus x. That's the same as minus x minus 1 over x, which is minus x plus 1 over x. So this looks again like minus f of x. So it is odd. Okay. If we found that neither of those conditions would be true, then it would end up just being neither. So let's take a look at actually, hold on a second. Looking back, my 85, I want to make sure that that's right. So looking back at the 85, it looks like there's actually a mistake in it. So 85 was a plus x squared here. So we should have had minus x squared should end up being plus x right at this point. So that should be a positive. And so actually the whole rest of it didn't come out the way that I expected. So this is x squared minus x. That actually makes this one neither, doesn't it? Okay, because it didn't end up x, f of x and minus f of x. So sorry about that, but it is fixed now. All right, so 87 will come out to be odd. I'll leave it to you to check that that's true. Okay. All right, so that was a bit about even and odd. What we want to do next is look at a couple of examples where we just determined what transformations were applied to a graph based on the formula. So here it says, suppose that the graph of f is given. We are to describe how the graph of each function can be obtained from the graph of f. So just to try a couple of these, f of x minus 1, you want to think about what the -1 would do. It would shift down by 1 unit. Okay, that would be one example. Let's try 9 and 10a. F of minus x, so we just got done talking about even and odd. So f of minus x, this would be an adjustment in the x direction. And so an adjustment in the x direction would be a reflection across the x axis. Okay, minus f of x, here we're doing the adjustment in the y direction. If we're doing the adjustment in the y direction, that is going to be across the x-axis. The first one was across the y-axis. So this one is across the x-axis. Okay. This can be a little bit confusing to think about that, because here, if we're changing the sign on the x's, if we're changing the sign across the x's, then that means that we're moving across the y-axis. So the names are kind of opposites. If you're adjusting the x's, then that means that it's across the y-axis. Here we're adjusting the y values, so the reflection is across the x-axis if the signs of the y's are changed. Okay. All right, two things happen in this one. The x minus 5 would give us a right shift by 5 units. And then additionally, it would go up by 2. Let's try these two. 3f of x versus 1/3 f of x. This would stretch by a factor of 3. The 1/3 f of x would compress by a 1/3. All right, so a couple of examples where we look at some transformations based on looking at the formula. Okay. In these next couple of examples, we're given a particular function f of x, and we want to apply a stated transformation to the function and write down the resulting formula. So let's try a couple of these. So 53, we're to take the function x squared and shift it down by 3 units. So that would be x squared minus 3. For 54, it's going to be similar, only we're taking this x cubed function and shifting it upward by 5 units. For 55, we're taking the function square root of x, but we're shifting it 2 units to the left. So if we're shifting it horizontally, that means that we need to adjust the x's, right? So we'll do this before the square root function happens. And since it's 2 units to the left, it will be x plus 2. So careful there. For 56, we have the cube root of x is going to be shifted 1 unit to the right, so it will be the cube root of x minus 1. Okay, for 57, we're doing 2 transformations. It's 2 units to the left and then down 5. So 2 units to the left, that will be the absolute value of x plus 2. So the 2 units to the left, that is happening in the x direction, so it's x plus 2. The downward 5 units happens after this absolute value, so it's a transformation in the y direction, so that will be minus 5. Okay, and then let's see what else we can do. Let's go ahead and do 59. We have the 4th root of x, which reflect in the y-axis. So if we're reflecting in the y-axis, that means we're changing the sign on the x's. And then we're also shifting it upward by 1 unit. All right, so there's a couple of examples where we were given a function and a transformation to apply, and we wrote down the transformed function. Okay. So in the next one, this next one's fun because it's just matching. We're given a functions graph shown here in blue, and we want to try to find out which of these other 4 graphs are the graphs of the transformed functions that you see at the top of the screen. So f is the blue one, and then we want to figure out which one, for example, is 1/3 of f of x. So 1/3 of f of x multiplying by 1/3 should make the graph 1/3 as tall, but not move it positionally or anything. So that would be function number 2. B, 2 things happen here. X plus 4 on the inside, that shifts it left by 4. And then we change the sign on the y values. So that moves the graph 4 units to the left, and then also reflects it across the x-axis. So that will be function number, or graph number 3 for B. Okay, for C, we have x minus 4. That will be right by 4 units and then up by 3. So relative to this f of x, the only one that goes right and up would be graph number 1. For D, we just have f of minus x. That will be this reflection across the x-axis, and so is function number 4. So given a graph, we're able to identify which transformation had been applied. Okay, so we're almost there. So in this, what we're going to do is we'll be given a function here, f, just a little triangle sawtooth function, and we're going to apply a couple of transformations to that function and see what the graph is going to look like. All right, so let's take a look. So we have 6 graphs here we're going to try. For A, we're going to take and find f of x minus 2. So the fact that this is x minus 2 says that we should shift the graph to the right by 2 units. So this was my original graph. So what I would do is think about where a couple of important points are. So the left point, which was at the origin, will now be at 2, 0. The pointy part at the top was at 2, 4. So now it will be at 4, 4. And then the intercept that was at 4, 0 will be at 6, 0. And then we're able to just simply connect the dots. So that's our graph of A, right shifted by 2 units. For B, by contrast, it's f of x minus 2. So that means that the graph is shifted down by 2 units. So we'll take our existing graph, look at a couple of important points, just move those down by 2 units. And then connect the dots. Downshift by 2 units. Okay, for C, this is 2f of x, so that means that our function values will all be multiplied by 2. If we're taking our x's and keeping them the same and multiplying the y's by 2, then that means that we are stretching the graph vertically. So the 2 intercepts will remain the same, but at the point 2, 4, it should now be 2, 8. Right, so that's more here. So this graph should look like it's been Just kind of elongated by a factor of 2. Okay, stretched vertically. For D, we're doing two things. We're going to multiply the f of x's by -1. That will reflect it vertically, so reflect it across the x-axis, and then push the graph up by 3 units. So we're going to reflect this downward. So let me make a rough draft of it. So to reflect it downward, it would basically look like that, reflected across the x-axis, but it needs to be pushed up by 3 units. So I'm taking those intercepts at 0, 0, and 4, 0. I push them up by 3 units, and then the point that got reflected to 2, -4 will be pushed up to 2, -1. Okay, so that will be our finished graph. Right there. Okay, for E, we're doing f of -x. So that means that we should reflect the graph in the x direction, so across the y-axis. So our x's will become negative. So this will be a reflection to -2, 4, and then -4, 0 for the other intercept. And then finally for f, we have two things going on. We have f of x -1, so that will be a right shift by 1 unit, and then the y values will be multiplied by 1/2, so it will be squished vertically. So right shift by 1, then make it half as tall. So right shifting by 1, I move the 2 intercepts. The multiplication by 1/2 doesn't change anything here, right? Because the y values are 0. 0 times 1/2 is still 0. But the y value, instead of being peaking at 4, it should now peak at 2. It will be half as tall. All right, so there's a couple of examples where we were given a function by the form of a graph and a couple of transformations to apply, and we applied all the transformations to those 6 graphs. And then that takes us to the end of section 1.5, which was about transformations. Again, I think it would be a good idea for you to practice some of these transformations using the computer, and then of course make sure to draw some by hand, just so that you really get a feel for how it's done. Also get used to that idea of even and odd as a criterion for a function to tell whether it's going to have a y-axis reflection symmetry or 180-degree rotational symmetry. In the next section, we'll go on to looking at absolute value graphs in more detail. If you have any questions, let me know. Otherwise, have a great day.